Hi friends, let's today we will start the homogeneous function. First we'll see the definition of homogeneous function. A rational integer algebraic function f of xy is said to be homogeneous function of nth degree of nth degree in x and y if the sum of indices of x and y in each term is equal. For example, f of xy is equal to x cube y minus 4xy cube plus 2x square y square plus x raised to 4 minus y raised to 4. If you observe here, in each term the sum of the indices in each term is 4. So this is a homogeneous function of degree 4. So we can find the degree of homogeneous function by using this definition. For example, x square plus y square upon root x plus root y. Let's verify whether this is homogeneous and what is the degree of these functions. So this can be written as, you can take x square common from the numerator and x to the power 1 by 2 common from denominator. And after simplifying this, x square means 2 minus 1 by 2. So x to the power 3 by 2, 1 plus y upon x bracket square divided by 1 plus under root y upon x. So this is the homogeneous function of degree is equal to 3 by 2. So in this way you can calculate the degree of homogeneous function. Now let's go for the Euler's theorem. So we see now the Euler's theorem. So this is for 2 variable as well as 3 variable. So Euler's theorem on homogeneous function. It states as if z is homogeneous function of 2 variables x and y of degree n, then the expression x dabba z by dabba x plus y into dabba z by dabba y is equal to n into function. N is the degree of homogeneous function. Means if the function is homogeneous, you can write this expression without calculating derivatives. Then we see the corollary 1. That means if z is homogeneous function of 2 variable x and y of degree n, if z is homogeneous function in x and y of degree n, then you can write the second order expression x square dabba square z by dabba x square plus twice xy dabba square z by dabba x dabba y square dabba square z by dabba y square, and you will get equals to n into n minus 1 times z. This is again for the homogeneous function. So this is the corollary second. First, now we see the corollary second. If z is homogeneous function of xy of degree n, and additional information z is equal to f of u, z is equal to f of u, then x times dabba z by dabba x plus y times dabba z by dabba y is equal to n into f of u divided by f dash of u. So this is the corollary. Without calculating this partial derivative, you can find the value of these expressions by using concept of this homogeneous function and Euler's theorem. Then x square dabba square z by dabba x square plus 2xy plus y square is equal to, this is g of u into bracket z dash of u minus 1. So here also the value of the second order expression g of u means this value n into f of u divided by f dash. You can find the value of this g of u considering here and their derivative. So what is difference in corollary 1? Z is homogeneous function of degree n, and here z is homogeneous function of degree n and z is equal to f of u. Means you will get the function that is a homogeneous expression. Now this can be extended up to 3 variable also, x, y and z. That's so easy. So before that, let's solve one example of depends on this. So if u equal to cosec inverse x to the power 1 by 2 y to the power 1 by 2 upon x to the power 1 by 2 plus y to the power 1 by 2 square root. Then show that the value of this expression y square equals to tan of u divided by 12 in bracket 13 by 12 plus tan square u upon 12. So you can solve this example by using concept of homogeneous function and Euler's theorem. Now consider this u equal to cosec inverse of this. So you can write the given function as cosec of u is equal to x to the power 1 by 2 plus y to the power 1 by 2 upon x to the power 1 upon 3 plus y to the power 1 upon 3 and square root. Now let's find the degree of this homogeneous function. So take x to the power 1 by 2 common from the square root. So x to the power 1 by 2 to the power 1 by 2. So in bracket there remains a 1 plus y upon x to the power 1 by 2, and in the denominator also x to the power 1 by 3 is common, and here in denominator also remains like this and square root. So here in the numerator x to the power 1 by 4 upon x to the power 1 by 6, and this as it is. Now if you calculate this, you will get x to the power 1 by 4 minus 1 by 6. So if you perform the calculation, 1 by 4 minus 1 by 6, 6 minus 4 upon 24, that is 2 upon 24, 1 upon 12 into bracket So this is a homogeneous function and you call this as a z. So z is equal to f of u, means in this form, x to the power n f of y by x. And so here we apply the corollary 2, as z is equal to f of u and x to the power n f of y by x is a homogeneous function. Z is homogeneous function of degree 1 upon 12. Now by using the corollary 2 formula, x dabba z by dabba x plus y dabba z by dabba y is equal to, or you can write in terms of u also, n into f of u divided by f dash of u, as it is f of u function. So n is 1 upon 12, f of u is cosec of u, and derivative of this is minus cosec of u into cot of u. So cosec of u get cancelled, so it is minus 1 by 12. 1 upon cot means tan u. So this is the first order expression for this. So to find out the second order expressions, so you have to differentiate this, but we are using the corollary 2 again. The value of, so g of u is equal to nothing but n into f of u divided by f dash of u is equal to minus 1 by 12 tan of u. And now to find the value of x square dabba square u by dabba x square plus 2xy dabba square u by dabba x dabba y plus y square dabba square u by dabba y square is equal to g of u into bracket z dash of u minus 1, and g of u means minus 1 by 12 tan of u. This value we can use here. Then derivative of minus of tan u, it is sec square u minus 1. So minus 1 by 12 tan of u. So sec square written as 1 plus tan square. 1 plus tan square u minus 1. And this can be written as minus 1 upon 12 tan of u minus 1 minus tan square u and minus 12 divided by 12. And so this can be written in terms of, so due to this minus sign it becomes plus. So again 1 plus tan square or 13, 1 by 12 tan of u tan square u plus 13 upon 12, and this is the proof which we required. Or we can write in another form, that is tan square u upon 12 plus 13 upon 12. So this is the use of homogeneous function and Euler's theorem to calculate this type of expression without calculating actual derivatives, higher order derivatives, and without only calculating the degree of homogeneous function, we can find the value of this type of expressions. Okay, thank you.